Oh, I'm so excited. The history of answering what forces plates to move is a farcical play on man's ability to reason. In short order, we will see reality become inconceivable and the absurd be accepted as factual. Recalling sutures at collision zones, oceanic crust and lithosphere are caught up in collisional mountain ranges. It's here we first sampled densities of oceanic crust and the uppermost mantle, what we know as the lithosphere. The problem? Cold solidified mantle is not hot pressurized mantle. Another problem? Subcrustal mantle solidified to the crust to make up what we know as the lithosphere. They didn't really know that back then. So let's see how they concluded. How do plates move? Why do they move? The first idea comes from Arthur Holmes in about 1930. The continental drift theory had already been proposed by Alfred Wegener back in 1912. Even though this idea wasn't entirely novel, it had been around since about 1526. That's right. About the time of Shakespeare, someone first proposed the idea of how South America and Africa could fit together like puzzle pieces and maybe floated like rafts or football players or something like that. But they just didn't have any good data. Much like Arthur Holmes, who only had all of these features, all associated with heat, to develop a theory which some still learn in school. But it's not just any heat. It's an extreme amount of heat at isolated locations around the globe. Now, geologists know about radioactive heating, but the transfer doesn't really work very well. It's insignificant. And conduction, touching, would equally heat everything and quickly cool the mantle, stopping the continual supply of heat to these isolated features. Arthur was looking for a continually refreshing heat supply. With two of the three ways heat transfers, of course he lands on a hypothesis of convection. It's based more on deduction than data. See, by limiting the possible problems that needed solving to just heat flow, he completely limited the possible explanations for every observation we can make about these features, where they are, what they look, how frequently they occur. But just by looking at heat flow, of course he was able to say it occurs by thermal convection currents of molten magma. Thus, volcanoes and mid-ocean ridges are deduced as indicators of thermal convection in the mantle. As mantle convection had to drag these plates into depths, smash others together, and continually rip others apart, Holmes correctly inferred that this had to be some sort of great transporting power. Now, Holmes made great connections, but really he lacked data to speak with any sort of confidence. Seismic waves are the same as sound waves. Energy transfers through mass by molecule-molecule or matter-to-matter collisions. For the vibrational pressure to continue, there must be some sort of density for the wave to move, which is why you may know the saying, in space no one can hear you scream, because there's no matter to pick up the vibration of your vocal cords. As a medium's density increases, however, we see a decrease in a wave's velocity. It's much like creating a chain of dominoes. Place them too far apart and they won't pass on the energy to fall over. Place them barely within reach of one another and the observed wave will be the fastest. Place the dominoes very close together and velocity of the observed wave will be slow, or what we call attenuated. We use seismic attenuation to help us interpret the cold and the dense parts of Earth's interior, looking for dense subducted slabs and hot magma blobs underneath volcanoes. The idea is the same as using ultrasound to look at internal organs or look for a baby. Focusing on the red here, these are high velocity. They are interpreted as very low densities, places depressurized, where gooey blobs of molten magma may easily move. At the left part here, we see a volcano drawn in. Yet over here, underneath what is the ocean, we have a rift. And the subducting slab kind of jumps out at you in green as a low velocity and dense material. There is even some blue over here. And it's surrounded by yellow, a slightly less dense but hot plasticky material that we can quickly conclude that plate subduction occurs because subducting plates are more dense and can displace the mantle. Yet we can garner so much more information from this image, such as changes in mantle density and how it controls the subduction on a plate. I mean subduction, its velocity, the velocity of subduction. The white dots pinpoint earthquake foci, locations where earthquakes are occurring. Using them to outline the boundary of the plate, we see changes in the plate's angle. In some locations, it's steeply angled, such as up here in the upper asthenosphere, and then down here below 410 kilometers of depth in the transition zone of the upper mantle. But then other places, it's leveling out. It's becoming horizontal. Subduction angle indicates velocity. The steeper the angle, the higher the velocity. The leveling out is a slowing down, and down here at about 660 kilometers of depth, the plate is doing what we call embayment. It's kind of pooling, it's gathering. Seismic wave attenuation also provides us the actual densities of Earth. Just like Holmes, we know the ocean crust is about 2.9 grams per cubic centimeter. Holmes and most geologists at the time, however, operated under the assumption that the mantle, the stuff the plate had to penetrate, was the rock at the suture, the other rock, which was 3.5 grams per cubic centimeter. We know this rock is the accumulation of crystals which continually solidify to the underbelly of crust through time, and often total about 80% of the entire oceanic lithosphere. Under these constraints of surface samples, the thought of a plate sinking into a density of 3.5 was highly absurd, and Holmes had to revere the current of mantle convection as a great transporting power, the great transporting power of Earth. Yet our current analysis reveals the subducting slab remains denser than the mantle until that great depth near 660 kilometers. Also, Holmes didn't have continual observations of the seismic wave attenuation, which could have revealed the mantle's convection speed. Our knowledge of the depth of the mantle tells us that the plate is always denser by about 0.1 grams per cubic centimeter, and that the asthenosphere is most definitely less dense than the entire lithosphere averaged together. The speeds of the mantle and lithosphere off the coast of Oregon are given here. Orienting ourselves to the plates, this one right here is the Pacific. This is the Juan de Fuca, which is currently subducting underneath the North American plate. To kind of take a look at a few features, these are the Cascade Range volcanoes, and this is the Basin and Range in western Oregon and in Idaho. The data here shows that the Juan de Fuca plate is outpacing the mantle, pretty much dragging the mantle along. Detailed studies further show that all plates have a faster current that they can drive shallow mantle convection. That's right, even the North American plate, as it is slowly moving 2.8 centimeters per year at the surface of Earth, is pushing the shallow mantle along. This is the complete opposite of Holmes's hypothesis. It just flips it on its head. With the lithosphere going so much faster than the mantle, we have to reject the mantle convection hypothesis. The current hypothesis suggests the asthenosphere first crystallizes on the crust, forming or growing the lithosphere throughout time, increasing density. Then, during subduction, partial melting takes place, removing minerals with a low melting point, which also have low densities. Gravity, then, is pulling a dense plate through lighter mantle, and it solves the quest for a force behind why plates move. And this force, we see it manifest itself in three ways on the surface and the interior of Earth. The first occurs at mid-ocean ridges. We call this ridge push, where the contraction from cooling increases density along with the lithospheric thickening to settle the plate off the mantle bulge at the ridge and onto the abyssal plain. Both sides separate away from the ridge from this contraction and lithospheric thickening, and the process takes about 5 million years. At the trenches and subduction zones, we find slab pull. The thickened lithosphere loses water to the surrounding asthenosphere once it's subducted underneath, and partial melting takes place to remove the low density, low melting point minerals, and the slab is maintaining its higher density through this process. At any given time, the lithosphere, the sinking slab, is at least 0.1 grams per cubic centimeter denser than the mantle. As plates subduct ever deeper, however, only by using seismic attenuation to monitor the slab can we observe the problem at about 670 kilometers of depth. Although plates continue to accumulate crystals and increase their density, they stop around 670 kilometers, here marked 660, where the mantle density suddenly spikes, marking the area of the lower mantle. This is a discontinuous change from the gradual change observed in the upper mantle, so we call it the 670 discontinuity. Had the mantle continued to gradually change, the plate might have continued to sink. Yet here, at this greater density, the subducting slab embays. It rests along this barrier to the lower mantle, where, although the velocity is higher, suggesting lower density, the material is also much, much hotter, and it's convecting. Just below the 670 discontinuity, we see a remarkable increase in seismic wave velocity shown by the redness here, suggesting that this area is being depressurized. Looking around for clues, the material below looks like stretched taffy. So is the lower mantle creating a suction on the embayed slab via lower mantle convection, which could also cause the depressurized material above, those red zones? We think so. Therefore, the fate of the subducted slab is embayment, piling up at the 670 discontinuity until it gets sucked down into the lower mantle by convection. I find it ironic that we're still trying to determine the fate of the subducted slab using and pinpointing and getting caught on excessive heat flux, just like Holmes. I cannot but wonder if our data here is wrong or misleading, just as his was. Yet again, we are concluding with the data that we have. Yet Holmes's issue was using deductions rather than data. Well, this is our data. This is a depth density profile. I present it here to reveal the change in density of a secant plate and mantle as depth increases, so that you can best understand how the densities are different, and also you can see the many discontinuities. Not having perfectly constrained plate mantle densities at depth causes some misalignment in some of these densities, but you can still match them up. The angle of plate, which corresponds to subduction velocity, also pairs with density difference at depth. Lastly, the regions where the three mechanics of plate motion occur. Ridge push up here at the top, slab pull, which pretty much occurs everywhere until the 670 discontinuity, and then slab suction. And to think, this is all happening now under the Philippine plate over by China and just south of Japan. If you go here on Google Earth, you'll find these volcanic islands and some of the volcanoes that are just to the east of the East China Sea. You'll be able to see these trenches here and this ridge. I'm anxious to see how many questions this raised rather than answered for all of you, because this just opens up so many ideas as to how we can understand our Earth and what's really going on beneath the skin of everything. But we won't be able to talk about them unless you write them down. So please take a moment, write down all your questions that you have, and bring them to class. But before we go, one quick review on the three tectonic mechanics. Note that this solution still can answer Holmes's concern for how features are associated with heat. By not focusing how to supply heat and collecting observational data on the Earth's interior, we solved his heat flow issue and proved that his once absurd conception proved to be a reality.